Lesson 8.3, Improper Integrals. What you'll learn about: infinite limits of integration, integrants with infinite discontinuities, tests for convergence and divergence. This section really is a technique section. Let's go ahead and give the definition of an improper integral. An improper integral has a limit, one of the limits, that might be infinity, or both of them. And we're going to take a look at how we deal with this. Let's first take a look at an improper integral like this one. What we're saying is we want to find the area under the curve as x goes to infinity. So this is an infinite amount of area. And we want to see if this answer gets closer and closer to a particular number, or if it just becomes so large without bound. But to do that, we're going to have to work with a finite integral. So we do this by replacing the infinity with a b, and this portion right here is a finite integral. We're stopping at b right here, so we have a finite amount of area. And then we allow the limit as b goes to infinity, and then this replaces this right here. Okay, so here's what the box that we had before. If this limit gets closer and closer to one particular number, we say that it converges, and the limit is the value of the improper integral. And same with number 2, but if the improper integral does not have a limit, it fails to exist, then we say it diverges. When we have two limits that are improper, we separate it into the two improper limits where we're dealing with a constant at least on one of the limits of integration. And both of these must have a limit in order for this integral to converge or to have an answer. If either one does not have an answer or does not converge, we say the whole thing diverges. Let's go ahead and jump into an example here. We have an example where we have the upper and the lower limits are infinity, and we're going to try to determine whether this has a limit. So the first thing we're going to do is between negative infinity and positive infinity, we're going to choose some constant. 0 is a great number to work with, especially when you're working with the fundamental theorem of calculus. So we're going to separate these, and we're going to go from negative infinity. We're going to allow b to get closer to negative infinity. We're going to go to 0, and from 0 to b. So we've taken this improper integral, we've rewritten it as two improper integrals, and now we're going to evaluate here. So we're going to take the limit as b approaches negative infinity, and the antiderivative is e to the x, and we're going to evaluate that from b to 0. So this is going to be the limit as b approaches negative infinity of e to the 0 minus e to the b. Now b is approaching a negative number, so it's approaching numbers like e to the negative 100, e to the negative 1000, and you know all of these are really very small fractions, numbers that are getting close to 0. So we can say that this is going to 0, and then the answer will be equal to 1. So this portion of the improper integral has a limit, therefore it converges. Now let's see what happens with this other one. So we're going to take the limit as b approaches infinity of antiderivative is e to the x, evaluated from 0 to b, and so this is going to be limit as b approaches infinity of e to the b minus e to the 0. Now right here we're going to have a problem because that is going to get large, and so this is going to go to infinity, and e to the 0 is 1, but that has hardly any effect on this whole process here. So this is not going to converge, so we say the whole integral diverges. It's not getting close to any particular number. All right, let's take a look at this integral integral, improper integral. How do I know it's improper? It has a infinity here. Let's get a picture of what's going on here. 1 over x looks like this. And what we're being asked is, starting at 1, and we're getting all of this area, will this area get closer and closer to one particular number, or is this just so much area that it grows without bound? And so that's what we're trying to determine. Okay, so I'm going to change this into, I'm going to go from 1 to infinity, dx over x, and over x. Let's see, 1 to infinity, dx over x. And I'm going to rewrite it as the limit. I'm going to replace the infinity with a b. I'll let b approach infinity. 1 to b of dx over x. And this part is the finite. So this is the limit as b approaches infinity. And this is going to be the natural log of x evaluated from 1 to b. Notice I didn't have to put the absolute value because I'm working with positive terms. Limit as b approaches infinity of the natural log of b minus the natural log of 1. Now this is going to be going to infinity because this grows without bound. So this answer is infinite, and that tells me that this diverges. So even though it's a little bit of area, it's really a lot of area, and it grows without bound. Let me put a triple star here because this is a very important integral, which we'll be discussing later and will be a part of a lot of tests that we look at. All right, let's go ahead and take a look at this problem. We're using partial fractions with improper integrals, so you're going to be able to use your techniques here. How do I know this is improper? It has an infinity here. So we're going to rewrite this, and what we're going to do is we're going to concentrate on this portion, the finite portion, and then when we can evaluate this, we'll take its limit later. So we're going to separate it. We're going to find that a is going to be 1 and b is going to be -1, and so we're going to have this. This will be the natural log of x plus 1 evaluated from 0 to b plus the natural log of x plus 3 evaluated from, oh, I should have put a minus here. Let's see, that was a minus. So equals the natural log of x plus 1 evaluated from 0 to b minus the natural log of x plus 3 evaluated from 0 to b. So this is going to be the natural log of b plus 1 minus the natural log of 1. And this is going to be minus the natural log of b plus 3 minus the natural log of 0. No, natural log of 3. Because if I put 0 on here, I'm going to get a 3 here. All right. And then this is going to be the natural log of b plus 1, and this is going to be 0, minus the natural log of b plus 3. And if I distribute my negative sign, that's going to be plus the natural log of 3. And then I think I have some more work on the next page. And I've done all of this. This is what I was doing on the last page. And I see two natural logs that are being subtracted, so I can say the natural log of the quotient plus the natural log of 3. Now, I'm going to take this expression and I'm going to find the limit as b approaches infinity. And we know that this argument is going to go to 1, and the natural log of 1 is going to be 0. And then as b approaches infinity, this has no effect on this constant. So this is natural log of 3. Now, since I have found that this integral becomes this, then I can say that it converges. All right, so let's take a look at using integration by parts. So when I use integration by parts, I'm going to substitute x for u, and dv is e to the opposite of x. And I'm going to take this portion right here, and I'm going to work with it and worry about the limit later. So I'm taking that and I'm replacing it u times v, evaluated from 1 to b, minus the integral of 1 to b, negative e to the negative x dx. So this answer is going to be negative b e to the negative b minus negative 1 e to the negative 1 minus, and I'm going to put a bracket there. The antiderivative of this is e to the negative x, and this is going to be evaluated from 1 to b. So now I have negative b all over e to the b plus 1 over e minus, and then this is going to be e to the negative b minus e to the negative 1. So this is negative b over e to the b plus 1 over e minus 1 over e to the b, and plus 1 over e. All right, so I have now an expression here that I'll be able to find the limit of. And so when I find this limit here, I am going to allow b to go to infinity, and when b goes to infinity, this portion right here, I'm going to be able to use L'Hopital's rule because it's infinity over infinity, and so the derivative of this will be negative 1, and the derivative of this will be e to the b, and this doesn't change. The limit of the sum is the sum of the limits, and as b goes to infinity, this is going to go to 0, and we're going to get 2 over e. So we took this improper integral, and using our techniques, we found that we got 2 over e, which means that it converges. Okay, evaluating another improper integral. How do I know it's improper? Again, the infinities here, so I separate them here. Again, I'm going to set up the limit, and then we're going to go say as a approaches negative infinity, and then this is going to be the integral of a to 0 of dx over 1 plus x squared plus the limit, and then I'm going to call that b. b goes to infinity of the integral of 0 to b dx all over 1 plus x squared. All right, let's go to the next screen. And right here, I guess I should take one more step. The limit as a approaches negative infinity, and this is the tan inverse, and that's tan inverse of x, and that's evaluated a to 0 plus the limit as b approaches infinity of tan inverse of x evaluated from 0 to b. Okay, now I think we can go to the next screen. And so when I evaluate these limits, remember what tan inverse looks like. This is going to be 0. This is going to be subtracting a negative pi halves, because that's what you're getting closer and closer to. And then this is going to be pi halves and 0. And then when we add these two pi halves, we're going to get pi. So we can see that this actually converges. So in summary, this is what we've been doing. If you have infinite discontinuities, you can sometimes have them at the endpoints, or you can sometimes have these infinite discontinuities within the interval, and if you do that, you just separate them. And this is the part 1 of this lesson.